So let me start our presentation today. Good evening, everyone. My name is Minki from Korea University, School of Electrical Engineering, and I'm responsible for the presentation today. The topic which I'm going to give is In the Shadow of the Hadamard Test, using the garbage state for good and further modifications. The paper is about Hadamard Test, of course, but the paper is not just about it. Its goal is to seek the further possibility of the Hadamard Test gate to improve the functionality in a manner of a software. So these are the contents for today. First, I'll explain what the Hadamard test is and prove its validity. Second, I'll introduce you 3 examples of how we can use Hadamard test in a different way. Third, I'll introduce you an example of how we can extend Hadamard test. And finally, I'm going to summarize all the presentation today. So let me explain why we need Hadamard test first. The necessity of Hadamard test rises with the development of quantum computer hardware. According to the paper, our quantum computing technology is on the edge of converting NISQ, noisy intermediate scale quantum devices, to ISQ, intermediate scale quantum devices, which means we need to reduce noise in the same time reduce the qubits needed. By doing so, we can get more efficient quantum computer. In that regard, Hadamard test is a suitable solution for the requirements. With these tests, we can get an expectation value of certain form of quantum states with only a few additional qubits. Also, in addition to primary way, there are few other ways we can use to reduce error rates. With classical mechanics introduced to the quantum computing process, we can approximate how the results must be. We cannot calculate the exact results, of course, but obviously it's helpful that we can determine the range of value it must be. Now let me explain what Hadamard test is. I would say this is the most important formula today, the formula below. Trace U raw. As you might know, U stands for the unitary operation and raw stands for the quantum state. In the quantum computing algorithm, sometimes we need the expectation value of the formula you can see. With Hadamard test, only with one additional ancilla qubit, we can calculate the expectation value of this formula. And let me explain in detail how the Hadamard test is validated. This is a visualization how the Hadamard test gate works. From now on, we call this part the part I marked with the red square, system register, and we call this one single qubit at the top a ancilla qubit. And in this presentation, I will use both terms, ancilla qubits and auxiliary qubits. And please be aware these terms refer to the same thing. So let's start with raw a mixed states. To obtain a state A, we'll apply Hadamard test gate to states, and with the attributional law, the formula will become like this, as you see here. And we move on to state B to apply unitary operation. Respectively, raw1 obtains U in front of raw, and ket1 obtains U dagger after the raw. With this principle, we can get this formula. You can see these raw0 and ket0 changes nothing. But these terms, the 3 terms after the formula, so let me explain like second term. It has ket1, so it has U dagger behind the raw. This term has raw1, so it has U in front of raw. Finally, the term, like the final one, it has both raw1 and ket1, so consequently, it gets both U and U dagger. So, okay, let's move on. So to obtain the next state C, we apply Pauli operations. So from the state B, we substitute its terms as written above, and this is state C. To get a state out, we apply Hadamard test once again, becoming this form. And now with some algebra, the probabilities of getting 0 and 1 are shown above. We subtract those 2 terms to eliminate traced raw term, and finally, we can get the formula with which we can interpolate the result, which means with measurement, we can get P0 and P1 experimentally. We know phi value, so we can approximate trace used raw. But the problem is these states, these garbage states, or which I call the system register. From the conventional Hadamard test, I would say, these states were used during the computation process, but didn't make useful information in itself. You can see the measurement is done only here, and all the other states are just discarded. You see the measurement symbol is just at the top qubits, and other qubits are all discarded or neglected. However, the author thought these states can be utilized also, implying us to further information in a direct manner. The idea is that we can extract some useful information in the shadow of classical physics. There are three possibilities suggested on the paper for the utilization of system register states. A, using system register measurement for fidelity estimation. B, using system register measurement for energy estimation. And lastly, C, using system register measurement for purity and eigenstatements. So let me start with A. It begins with the measurement of the auxiliary qubits of the output state raw out with the Pauli Z basis. It's a first formula, and then we can get the real part of this formula. But let's say we substitute the identical operation with single operation O as a measurement. Then it results in the second formula, the expectation value with O included. This can be even more extended to the linear combination of operations. To see the utility of this formula, let's say the measurement O is cat psi brab psi. I'm saying we set the measurement O as the rank 1 observables. And then we can rewrite the previous formula like this, the third formula. Once again, we assume that the cap psi is a pure eigenstate of H with known eigenvalue E. We get this formula, the last one, being able to separate into those two terms. You can see the real terms are separated into cosine terms and F terms. With this result, we can evaluate how how less the error occurred. So, and then we proceed to B. So far at A, we have used global shadows of the post-measurement state raw Z to extract information about fidelities. Now at B, we will discuss how to trace out the auxiliary register to obtain raw I. According to the definition of tracing of the auxiliary register qubits, with algebra, we can see that the raw I equals to raw plus U times raw times U dagger O. Over 2, yeah. So this is the formula. You can see at the dots, you can see the final result here. Raw I equals, yeah. So Now at this formula, we apply certain Hamiltonians to both sides of equation. Also, we assume that the U equals linear combination of UI, which is E squared I times A times TI. And the following formula, the last formula, is valid. The result equals the energy expectation of raw. So in the previous process, we contemplated the equation with identical operation. In addition to which, we can calculate with various computational bases, x, y, and z. These aren't in itself meaningful, unlike the formula with identical bases. However, in my opinion, with further research, we can know how to utilize these formulas also. In conclusion, we can prove that we can get an expectation value of energy from Hadamard test without further resources. What we all need is just some more additional measurements. So on top of that, we can get the formulas still unuseful, but has further potentials. Now, final utilization example of system register C. This is more picky to use, I would say, and let me explain why. From the formula from B, we scare the raw I, and this is the equation we get, you see here at the presentation. In this formula, if the result is near 1, we can say that the raw is a pure eigenstate of U. This way, we can measure the purity of the quantum state. However, this process requires exponentially many copies of the states. This is because to estimate this term here, trace of raw square, we need to measure them, but multiple ways, multiple samples to obtain credible value. This is why the author called this application part C interesting but not useful. Okay, so till now, we primarily discussed about the further utilization of system register of Hadamard test. Now we will modify the Hadamard test logic by adding another component, anti-controlled unitary W. Here's a comparison between conventional Hadamard test, gate logic, you can see at the left, and the test logic with W component added. You can see it on the right. You can see between unitary operation and Hadamard gate, the W operation is connected. This is a comparison of formula of raw out without W component. You can see on the left, and this is a formula of raw out with W components added. You can see arbitrary gate W is replacing the identical logical gate I. In this way, we can modify the Hadamard test further only by adding one gate, being able to extract more information from one single test. Let me give you an example where this modification is useful. We will consider U equals E square IHT1 and W equals E square IHT2. We can see these results are plugged in. When we do Pauli Z operation, we get this formula. You can see red arrow. We set raw equals cap psi, prop psi with energy E given as above, and we move on. However, we get a trace operation, and this is what we get, the second term. So, but when raw is not an eigenstate of H, and cap psi is separated into linear combination of two different eigenstates, ket mu and ket v. It's a second red arrow, you can see. And let's say when ket mu and ket v has different energies E1 and E2, and then we can rewrite this formula into this form, the last one. In this way, we could separate the trace value into two cosines. This is one of the application, and further utilizations are possible. So with this application, we could separate the one quantum state into two different eigenvalues. So this is all I've prepared, and I'll give you a brief summary of today's journal pub contents. First, we studied what is a Hadamard test and what it is for. Hadamard test has this form of circuit. You can see the picture. And the final goal of Hadamard test was to get this value of quantum states, trace of U raw. But we took a step further from here. The author was trying to find out can we use the Hadamard test in a different way. There were two methodologies using existing system register, the red arrow on the right, and the adding certain gates, the red arrow on the left. For system register case, we have three specific examples: fidelity estimation, energy estimation, purity, and eigenstateness. For adding W gate case, we had one example, eigenstate separation. Okay, so through this journal club, we seek for further information from existed well-known quantum circuits. Accepting the further information that has been ignored so far led to sophistication and increased efficiency. We could verify this form the part we used in the informations from the system register. Also, we could see that with slight modification of the circuit enables many new applications. We check this from the W gates added to the Hadamard test. Conclusively, it is obvious that the quantum computing can be improved with algorithm improvements. This study implies the same methodology from this paper can be applied to many other algorithmic subroutines. So yeah, this is all I prepared for today, and thank you for listening.